It's a pleasure for me to introduce Alexander Balatsky. He hates being introduced, but nevertheless, I had to give a little introduction. He cannot do anything about it now because the guest. He has to be very nice to me. His coordinates can be anywhere in the world. We have seen that where is Carmen Sandiego? You see that to show it is there. She comes. Nobody knows where she is. Like that. We can never find Sasha anytime, any given place. We can just happen to bump into him. We cannot look for him. So he is in U Connecticut. His base is director of Anomalous lab, and he's also at Nordita in Sweden. And he doesn't like the weather in Las Vegas. He flies to Sweden in the winter. So he has done extensive amount of work on many fields. He's having got himself educated in Lando Institute. You can imagine what he starts out with. So my association with him is through his papers in superconductors. Phonons is one of the most complex interface one can think about. He has done pioneering work like some time ago. So here he is talking about the Dirac Materials and future statistics and so on.
Okay. Right, thank you. So it's certainly very interesting to be here. This is a very interesting format where you run the visitors through two big places. So I'm at the tail end of my energy trying to continue to be to absorbing the information, actually. So it's wonderful. Thank you again for this opportunity. Couple of things. The title is misleading. This is autocorrect on the phone, not this title. The title given on in the corridor. It was something about the status and future perspective, but I was typing on the phone. Autocorrect decided that the statistics, and that's how it went out. And so it's my issue with the quality control when you do these things like on the small screen. So what I'd like to do is I'd like to discuss Dirac Materials and organic materials database. Here's Dirac, who got Nobel Prize for Dirac equation in 1933. And the idea is actually it's a class of materials that we kind of know what it is. They have all this linear dispersion and this unusual behavior of the crossing points in the dispersion curve. And then I will attempt to define what Dirac materials are. I'm pretty sure the people here and at MIT know what Dirac material is, but nevertheless, let me actually attempt to define it a little bit. And then once we define it, the question is, so what? The idea would be that for this concept to hold, it would be good to have some predictive component to it. In other words, basically, if it works, then what exactly it helps me with if I find a new material? Is there some predictive, very simple qualitative statements you can make once you establish that the material is Dirac or Weil, okay? Then, and the one example where I'll show this universality of the response of Dirac materials would be the local defects, response to local perturbations, which is very different, I presume, from majority of the work you've seen or related to maybe work on the STM in Jenny Hoffman's group here and elsewhere. And so that's actually one part. Then I will touch briefly on the Dirac bosons and magnons, namely the Dirac materials class can be extended to include fermions and bosons. It doesn't extend to bosons. It doesn't have to be only fermions. And then the part of my, if you want, advertisement tour, so I'm wearing here a little bit of advertiser. I want to show you the database, organic materials database we've been developing for the last 2 years. So this is a relatively new thing you might not know. So, all right, let's start. The work obviously is funded by, in the US and the Department of Energy, and there is some foundation funding actually in Europe, okay? So if you look back, the way I noticed it, my PhD thesis was on helium-3, superfluid helium-3, where we use routinely to look at the quasi-particle Bogoliubov-Dejean equations that look like Dirac equations. And then if you look now recently in this explosive growth of the class of materials, or set of materials which have this unusual Dirac properties or Weil properties. This list is growing very rapidly, so I will just point out that Dirac materials, Dirac excitations or Weil excitations can be hosted in the copper oxide plane, which is a place where we have presumably the core component of the D-wave superconductivity or unconventional superconductivity in cuprates. We have a graphene sheet, which host Dirac excitations. The surface states of the topological insulators hosted. And so qualitatively, people say that Dirac material is something where you have maybe a linear dispersion, where instead of parabolic dispersion, you have a linear one. I would say that probably requirements are a little bit tighter and stringent, more stringent than this, but it would go. And so let's just kind of go with this for now, and then we'll try to tighten up what I mean by Dirac materials. Okay? So the question is, if I have a set of these materials, is there some common set of statements you can make? And I'd like to convince you that yes, there is a common set of universal properties you would expect from Dirac materials. And then the common language for this would be DM, Dirac materials. Okay, so just going to do this. There is a framework that might hold us basically and have our thoughts organized, help us to organize our thoughts. So let's start with fermions. Yeah, so all right. So with the fermions, I think actually this what I'd like to say is if you look at the discovery of Dirac equation, I should probably pay homage to Dirac for his beautiful discovery of Dirac equation. The slide is missing, and so I will just tell you in words. Okay. So what's happening is that back in 1928, he wrote a paper about Dirac equation. And the idea was to develop the equation that would respect Lorentz invariance. Start with the Schrödinger-like equation, time evolution of the wave function that would describe the behavior of the wave function in real space. And what he noticed is that you cannot do this with the Schrödinger equation because it expressly violates Lorentz invariance. The scaling and time dependence, the scaling and momenta is different. You have a quadratic kinetic energy, you have a linear time dependence, linear derivative in time. And so what he noticed then that you need to generalize this equation to something that would be looking like a matrix equation. And so he invented Dirac matrices that go as a Dirac, so like as a product of this Dirac matrix with the momenta, and effective Hamiltonian, what turns out to be essentially matrix equation, which has a linear power in momenta and linear power in time, and therefore, or in frequency, and therefore would explicitly respect the Lorentz invariance. The price to pay for that was if you're dealing instead of scalar wave functions, you're dealing with the matrices. You have two component wave functions. And so one component of this wave function would be, say, coding for one set of particles, and another component of the wave function would code for something else. So the very fact that he had to leapfrog from the scalar equation to the matrix forced him to actually declare that there is another entity out there. If you have like a spinorial wave function, part of the spinor would describe the fermions, electrons, and part of the spinor would describe some other particles. And so I'd like to say there is a nice slide which I missed for some reason here, that essentially the prediction of antiparticles in the context of Dirac equation was very naturally following from the fact that it was a matrix equation. You have two components of the spinor. So parts of the spinor were coding for particles, some were coding for antiparticles. And that's what he got a Nobel Prize for. So he wrote the paper in 28, he got a Nobel Prize in 33. This is explosive time of this, explosive time of the development of the quantum mechanics. All right. Then for us, the Dirac equation is very important because, for instance, it describes behavior of relativistic particles in solids. And it's also very important because it captures the role of spin-orbit coupling. There are all sorts of very interesting effects, like Zitterbewegung-Klein paradox, which you've heard about in the context of Dirac equation, which we apply to quasi-particles in graphene and others. Now, so having said that, this is a very important equation. I'd like to say the Dirac materials are kind of built on the universality statements, are built on the fact that there is equation, but nevertheless those are real materials. And so obviously you can push the analogy, but only up to a certain point. There are certain points where actually you have to remember that those are real materials. So for instance, if you look at the X-ray of Dirac material, right, they will look different because underlying crystal structure of them could be very different. I showed you one of them was, some of them would be square lattice, would have a square lattice, like this copper oxide plane. Some of them would be hexagon. honeycomb structures, and so on. All right, so then if I'm attempting to classify this and say that we have a subclass or whatever category of materials called Dirac materials, then the question is what exactly one would expect from this general classification. So I would point out in this context the previous were very robust and very useful classifications built up by Carl Linné. Now that since I'm in Sweden, I had to learn a little bit about Linné. And what's interesting is that very early on, back in the 18th century, he developed a very interesting binomial nomenclature system where a kingdom, I think genus, kind, species, where you come in and you essentially assign to this fork, actually, where you're going, you assign essentially binomial numbers. And it allows very simple, actually, tree of where you are in the, say, animal kingdom. Then what's interesting also is that it's robust, it's very simple, and it's also predictive. And the way I say it is that if you discover somebody goes into the jungles of Amazon and actually discover the new kind of spider with 8 legs or something, and then actually there are some whole set of other attributes which are following from the fact that this is a spider. Okay, so the idea is actually from any classification, what I'd like to extract also is this ability to essentially economize the thinking and get some useful predictive statements we can extract. Okay, so with that in mind, let me point out the very often used way of classifying, if you want, chemistry and physics in our community, namely periodic table of elements. And certainly you can have metals, you can have non-metals, you can have, say, magnets or magnetic, so like elemental magnets actually residing in this periodic table. The point is that Dirac materials, they don't have a single provenance. There is no single part of the periodic table where Dirac materials are residing. Okay, so it's a very different way of doing it rather than actually looking at the chemistry. So for instance, as I mentioned, carbon, which forms graphene, is a Dirac material. So graphene is a Dirac material, so carbon is sitting here. I mentioned bismuth selenide, so you have some of the chemical elements that forming Dirac materials here. I have a YBCO, high TC superconductors. So there is no single place here, and the idea is what it is sort of like a functional property. Right? So it might be interesting to you, then you pay attention to this. It might not be interesting to you, and then you don't pay attention. But the idea is that actually there is no single class of materials in chemistry, chemistry-related one, that delivers you Dirac properties. All right, so what is Dirac material if to build up? For the purposes of, let me do a two-step thing. And at the end of it, I'll tell you I still don't quite know what exactly completely Dirac material is. But if I were to look at this as a sort of first step at what I would define as Dirac material, I would say it's a material where we have dispersion reasonably close to chemical potential, reasonably close to sort of low energy excitations that requires a metric structure with linear crossing point. Okay? Doesn't have to be linear crossing point, for instance, but nevertheless, basically what's important is that actually you do have some metric structure, and therefore the wave function here would be spinor that describes the multi-component wave function. Okay, then if you're lucky enough and you put the chemical potential right at the crossing point, density of states of these materials will be a power law, which is very different from what you expect from the metal. In the metal, for instance, when you fill up, density of states is constant. So then another universal property people mentioned in this context would be the shrinkage of the phase space would lead to specific heat, which would be dependent on temperature with a power which is not typical for the metal, for instance, T squared or dq. There is a story about minimal metallic conductivity, and I think Philip can tell quite a bit more about this. The story about the missing pi, what the conductance was in the two-dimensional metals, in the two-dimensional sheets of graphene. In a way, this was interesting, but I would say probably not very basic challenge. You might disagree, Philip, but I think actually the two-dimensional metals, two-dimensional systems inherently have a conductance at the level of E squared over H. And then this number obviously depends on the detailed properties of these sheets of the 2-dag we're looking at, the two-dimensional transport. The fact that the spectrum is linear would lead to the fact that you have Landau level scaling as a certain index with the number of Landau levels, namely square root of n. And this is a pretty universal consequence of linearity of the spectrum. Where I come in, I'd like to point out something. So there are all these universalities, or like general properties you would expect from graphene, where I would like to come in and tell you, namely that any of these Dirac materials can be viewed as the marginal semiconductors. And therefore, they're prone to forming these impurity resonances. So if you put defects in, very often inside these nodal points, you can get impurity resonances. They might be bad for you, they might be good for you. For instance, if you build a sensor and you put defect, or like, then you have the changes before and after, which indicate that you have a, say, molecule absorbed on the surface of graphene. Or it might be bad. If you're trying to build a very nice, very clean conductor, these defects would be so like something of a headwind. You have to deal with them.
So you're assuming that the dispersion is linear in all directions?
Yes.
It could be linear only in some direction?
So then one can do linear quadratic, linear cubic, etc. Yeah. So right now, let me go with the linear one, exactly. But I think it's an excellent point that there could be some other ones as well. So in a way, I do feel strong that there is some universal features, but then of course, if you distort the Dirac material up to, say, linear quadratic one, the changes will be made. So, but I think actually this provides a general kind of good starting point. But it's not a religion. We can adjust the definition as we go. All right, so then let me just build up a little bit better kind of classification on this thing, or try to tell you what the differentiator is. Take a metal. You have three-dimensional band structure. You have energy as a function of three momenta, kx, ky, kz. And you're saying if it's a metal, I ask computer to find out the locus of points, set of points where energy for particle hole excitation is 0, right? So if I have three parameters for the function, I quench one with one constraint that energy should be 0. For the three-dimensional system, I will have generically a surface, which is named Fermi surface in the metal, hence the name. Now, for Dirac material, actually, I will have the same set of particle hole excitations, and I have the same sort of like related to this particle hole excitations, the properties like plasmon excitations and so on. But nevertheless, what's interesting is that the codimension of nodal points in Dirac will be at least one less than in the metal. So if the Kohn-Sham would predict that the metal should have a surface, I will have a point or a line. And if in 2 dimensions, the theory of metal would predict I should have a Fermi line, I can have a point. So it is obvious that going from d minus 1, this 2-dimensional surface in 3D, to something which has a one whole integer dimension less is not an accident. You just cannot do it on accident. There is clearly something else going on. And so what's happening is that this massive reduction of the zero energy or low energy excitations is coming because you have either symmetry or topology that forces this particular property of the band structure. Just an example. What you can see in the Dirac material is that you have essentially very stable and robust crossing point that is not changed unless you work hard on this or unless you break the symmetry. So there is a typically, actually, there is a symmetry that allows these terms to cross. And that's what the utility of Dirac materials could be. That if you have a symmetry that actually allows me to sort of open and close the gap, then actually I can take advantage of the symmetry. I can functionalize the response of Dirac material by closing and opening or drastically changing the properties at the nodal point. So the symmetry for graphene, well, depending on, for this conversation, let me say that you have an A-B sublattice symmetry that forces degeneracy point. For the case of D-wave superconductor, it's a much more complicated symmetry. It's a symmetry that involves rotation by 90 degrees together with some gauge transformation of the order parameter. I have to change the sign of the D-wave orbitals or D-wave gap, superconducting gap. In the case of the topological insulator, the crossing point comes as a result of the essentially strong spin-orbit coupling that forces the direction of the particle momentum to be tied up to the value of the spin, and so therefore these counter-propagating modes have exactly opposite spin. All right, so then As I said, the utility of these Dirac excitations or excitations near this nodal point is the fact that I can open and close the gap, I can modify the states in the vicinity, and the other one, probably less important, but important for the transport and other properties, is that these materials will be inherently less lossy. You do not have as much space, phase space for particle Hall excitations, and so those lead to the decoherence, and so Dirac will be useful for this. As we were writing this review, we found out that there is a growing list of these. So if I come up with some classifications, obviously, it would be good to have more than 2 or 3 compounds I looked at, right? So, but I think by now it's very well established. Let me just quickly go through. We certainly have a graphene, silicon, germanium, where we have this Dirac physics very widely, very clearly present, and the energy scale of about 3 electron volts. We do have artificial graphenes, where the energy scale could be very, very tiny, could be microvolts and below. So we have hexagonal layer heterostructures, and so on and so forth. We do have a 2-dimensional topological insulators. We have a 3-dimensional topological insulators where we have the Dirac points. I would submit to you that actually D-wave superconductors or even helium-3, all of them are Dirac materials at low enough energies. And then, so you can have a while in Dirac metals. So we wrote this review, and then since then, there is a clearly rapid growth of the class of materials which shows the Dirac points both in 3D and in 2D. I just looked around and found out that there is a whole book called Dirac Matter now, published I think in 2016. Just to build up for what I want to tell you at the end of it is majority of the entries in this table are inorganic compounds. I just point to you that you do not hear beyond graphene too often about organic Dirac materials or organic topological insulators. So that's a space towards which, actually, with this in mind, we build this database that will provide the searchable tool. I'll show you. All right, now, obviously, it's very important to acknowledge that there is some very exciting development in terms of the wild fermions or wild physics. So for purposes of my universality, wild does satisfy exactly what we ask for Dirac, and so I'm not differentiating. Obviously, in the context of a condensed matter system, when you have these two degenerate points split up, Dirac is essentially double degenerate wild. If you have these 2 points split up, there is experimental consequences. Okay, but I just also want to point out that wild equation was a change of the basis for Dirac equation. So it doesn't have its primalcy on its own. I think actually it's very, very closely related to wild. And as we can see now, there is this whole set of materials that have a wild points, but also a whole set of materials which continue to show the Dirac physics. Okay, so whenever I say Dirac, to a large extent, actually the same set of statements apply to wild, and I don't differentiate between them. So this is actually, a lot of this is universal statements for Dirac and wild. Okay, now, again, to point out that whether my emphasis will be on the local physics, there is a counterpart to this, namely long wavelengths, long time description that leads to the very interesting hydrodynamic properties of Dirac matter. And I just point out that if you look at the literature, it turns out that there was very interesting hydrodynamics of Dirac matter written back in 1957. And I know that I spoke to Leonia, and there is a whole set of very interesting hydrodynamic statements about the behavior of Dirac fermions in graphene done both at here and at MIT. Okay, so I want to go in the exactly opposite direction. So in addition to the universality of the hydrodynamic statements, I want to go to very local properties, and that perhaps would be something different. Okay, so I try to build the concept. I'm telling you that it's universal. So now I want to show basically universality in the specific examples. And the track I chose is the response of Dirac materials to local perturbations. Okay, just to recap the logic. So this is an example of STM image of the single impurity in the D-wave superconductor. This is zinc substituting the copper in the square lattice of a copper oxide plane in high TC. We know this is unconventional superconductor because of the D-wave lobes. So there's a Fermi surface. I have a D-wave lobes, gaps, which go from plus to minus, and every time you go from plus to minus, you have to go through the node. I have a V-shaped density of states. And then every time I put a defect in, I have a resonance coming in and filling up the, coming inside the gap. So if I put in defect, it's clear that actually if I have unconventional superconductor at some concentration of defects, so in this case it's a simple scalar potential of the zinc side on one impurity, then I can look at the scattering of the conduction electrons of the side, and we'll find out that there is this resonance moving in. So in itself, it's a very natural. You have a marginal gap semiconductor. This gap is not very wide. It's about 50 millivolts in range. And then if you put strong enough impurity, you generate the resonance. If you generate many of them, you fill the gap. And if you fill the gap, you kill superconductivity. So that's what's really happening. You probably heard about Anderson theorem and the suppression of TC. But if you ask actually what's happening if you don't have a finite concentration of impurities, I put 1 or 2 of these pair breaking impurities, bad impurities for superconductivity. You can inflict the damage everywhere, but you do the kind of local damage, and you're producing these impurity resonances. They have a net effect, detrimental effect of filling up the gap. Put it differently, if you're coming from semiconducting world, it's essentially a small gap semiconductor, and defects build impurity band. Nothing surprising, okay? Now, so what we were looking at was a slightly different aspect of it, namely this alignment of the, if you want impurity resonance. This resonance has energy, but it also real space shape, and will be aligned with the nodes of the gap, and therefore you can probably make a guess about the nodal structure of the gap, because gap works as a retention wall. Right, so if I have, for instance, water, and if I drill in 4 holes, that's along these kind of directions, the water would leak out. So this impurity resonance will have a cross-shaped state, cross-shaped form. The energy of this resonance for this particular calculation trends to 0 as the strength of impurity grows. So the harder the impurity is, the more ultraviolet, the stronger the impurity scattering is, the softer is the resonance. This is a very, very non-metallic response. So that's another example of the Dirac physics, actually, that you do this very, very strong impurity, and you're producing very low-lying resonance. Okay, this is another example of universality. And sure enough, soon after, Shuheng Pan and Seamus Davis were able to image this resonance. If you look at the STM, so in the blue line, so blue line here is the DIDV tunneling spectra, taken away from impurity, and as you move your STM tip and actually position right on top of impurity, you see this kind of very sharp resonance. So I presume I don't have to tell you what the STM is doing and how it works. You have your local experts here, but basically the idea is that it's true that on approach to impurity, you have this collapse of this gap coherence peaks, and you have a very sharp resonance showing up. Okay, and at the time, we thought that's it. This is interesting, but okay, time to move on. Then actually, by the time I paid attention to graphene, a lot of the calculations were done. But what I found is there are some universal, there are similar, very similar impurity resonances in graphene. And therefore, so let me show you this. Therefore, it basically at least got me interested in the fact that maybe it's not the property of the Dirac superconductor. Maybe any nodal metal or any nodal state will produce resonance. So let me show you the example of graphene. Graphene comes out very clean. And so they had to work hard. This is data from, this is data, this is not the theory plot. This is experiment from the Madrid group, where they do the ion radiation of graphene to create the vacancy. So they knock off with ions the carbon atoms out of the graphene network. And this local resonance is clearly shown there in the STM. So here is the sharp peak of on the impurity side or on the vacancy side. And as you move away, you recover a nice, beautiful V-shaped structure, V-shaped density of states. The structure, the intensity pattern could be very different compared to the cuprate case, to the square lattice, but nevertheless, impurity resonance is clearly there. Then, impurity resonance is also seen in Dirac Material in topological insulators ubiquitously. So even though a topological insulator is supposed to be very protective against backscattering, you do have impurity resonances showing up. So therefore, actually, I will just put it out there. My point is that there is a robust universal response of Dirac materials to local perturbations. Namely, if you take graphene, if you take a D-wave superconductor, if you take topological insulator, in all of them, you have this impurity of states inside the node or near the Dirac point. Yes? That one? Okay, so this is graphene, this is vacancy, non-magnetic. This is zinc, which is non-magnetic. This one is less known, but this is unpublished data by, I forgot whose data is it, but basically they were telling me there might be iron, actually, impurity. Might be magnetic here. From the point of view of generating resonance, no. I mean, obviously, you have to pay attention to what's happening in the spin channel. But if you put a foreign atom, in fact, this is a good point. If you put a foreign atom, you always bring in actually quite a bit of different electronic orbitals. So if you want to model it in some effective Hamiltonian, you have to take care of the fact that actually electron not only can do this exchange, for instance, exchange coupling, but also can do scattering of momentum because you have a foreign object. So it's not only magnetic coupling, but also the scattering of the site itself. All right? Yeah.
You said it's a non-magnetic in the case of graphene. You see there is vacancy
Yeah.
there. How do you treat this as a defect?
I just put it in energy cost of sitting on the site to be infinity. You can first of all, you can solve it for the vacancy problem. You can say that actually I forbid any electron to hop on this site and numerically solve it. Or I can put in as a potential where the potential energy is so large that it guarantees that none of the electrons will go in there. There are many ways to do this. So there is you can do it just numerically, actually put in vacancy in the lattice and solve it. Okay, so now we kind of need to speed up. Okay, so let me show you so given this, if I get this suspicion that a lot of Dirac materials have this field gap and magnetically doped topological insulators, I'd like to bring this to the discussion of magnetically doped to the anomalous quantum Hall effect, the stability of the phase. So for those of you who know, the story was that if you have a topological insulator and if you have a Dirac state on the surface of it, when you put in magnetic impurities in, what you can think about is that this Hamiltonian, in the case of magnetic impurities which are ferromagnetically ordered out of plane, what you have is essentially the behavior of this is a Hamiltonian that looks like a spin in the magnetic field whose component has a kx, ky, and a z component. So in the presence of without this term with sigma z, this would lead to nice Dirac cone on the surface states, and those are well established in the case of the pristine topological insulators. But then with magnetic order, it was argued that it will open a gap. And you can see that the gap opens up in the presence of the ferromagnetically ordered impurities on the surface of topological insulator. Okay, this is example, actually, the figure drawn from the science paper by Kikun Shi's group, where they discovered the anomalous quantum Hall effect. So what I'd like to point out is actually where I'm going with this slide is that I will tell you that there are impurity states. There is no gap, but there are mobility gaps in topological insulators. Okay. So let me show you this. So the logic would be something like this. In case if you have a time reversal breaking, and say I have a bulk doped with magnetic impurities Ti, and all these magnetic impurities ferromagnetically ordered, I open the gap. Therefore, in my calculation for the Dirac spectrum for the surface state, I will have a gap, which is shown here as a sharp drop in the density of states because of magnetic gap opening. And then on top of it, if I recall that I told you that any defect inside the Dirac material produces resonance, what I need to do is solve the problem where not only I have magnetically open the gap, but I have to look at the scattering of this impurity site. So you cannot bring the foreign atom, like you cannot bring the iron atom into the matrix of the crystal without actually ignoring the fact that actually it has to scatter off this side. So it's a foreign atom. In addition to magnetic exchange interaction, there is a sort of like a potential scattering term. And this potential scattering term will generate this impurity resonance inside. As long as the potential part will be larger than exchange, this resonance will always there, always will come. And so you have one impurity, you have one resonance, you have two impurities, you have two, etc. And eventually, when you have a finite concentration of them, you will fill the gap. And so my suspicion, not suspicion. My statement is that for the strong enough potential scattering, you will have a gap filled in. You might have a remnant of this gap, but otherwise it will be completely filled. And it is true that to date, there are very few STM experiments that show the real gap, and I'll show you in a second actually the exception, or like cases where the story is more complicated than this. But it is true that if you look at the with STM spectroscopies, if you look at the spectra on the defect and away from defect, so what's shown here in the bottom part is a paper with Paolo Sessi from Würzburg, where he did the systematics of the density of states as a function of position for different impurities in antimony telluride topological insulator. And what he was showing is that what looks like the gap spectrum, if you zoom in, it clearly has a finite conductance. And these bumps are presumably related to impurities filling the gap. All right, so then more recently, we've done the more complete search, or like calculation, combined theory and experiment, actually, analysis of what's happening. And the story is more complicated. For three-dimensional vile metals, the defects might be close enough to the chemical potential, and you can have these impurity resonances clearly seen. But sometimes, for instance, like in the case of the manganese, there is very little modification of underlying density of states, even though there is a projected particular density of states on manganese near the chemical potential. But in overall profile, shape of density of states, it doesn't show up. So it is true that in magnetically doped Ti or magnetically doped vile metals, you can have something that looks like almost a gap, but in fact, actually, it will always be finite. There is no gap opening. So I would say that this is a very interesting, to me at least, it's a very interesting example of knowing what the response of Dirac materials was in the case of the D-wave superconductor and graphene to defects. I can tell you it's very unlikely that there is a true gap in magnetically doped topological insulators. It is very unlikely that there is a gap. Put it differently, the story about magnetic gap, magnetically induced gap in topological insulator is very likely subject to revision. All right, why? Well, let me just back out for a second. If you look at the 80s, I found some foil, probably it's a copy of the foil. If you look at the Landau levels, in the case of the two-dimensional electron gas that exhibits synergy quantum Hall effect, not even fractional. We have Landau levels in magnetic field, and when we put disorder, these Landau levels broaden. They acquire the finite width because of the disorder scattering, but nevertheless, actually, there is the bands which actually hold the conducting states. And then actually you have in between this, you have a mobility edges where you have a localized states. So you do have a finite density of states, but you have no mobility of the states. And then when you put the chemical potential in between, so like in one conduction band and another one, you change, this results in if you change the, say, magnetic field or doping, you're going from one Landau level to another one, you change the sigma xy. That's how the transitions occur in the quantum Hall effect. But for very clean 2D examples, actually, in the presence of magnetic field, nobody would talk about the real gap in between Landau levels. There are mobility gaps. And so we're in the world where words do matter. Actually, I would say that there is no gaps in the magnetically doped topological insulators. There are mobility gaps. Okay? So just to sum this part, I would say that anomalous quantum Hall effect was discovered in 2012. So one group which came out very early on with a claim of anomalous quantum Hall effect is Qi. What they point out is that to get the quantization, they need to cool down samples down to 30 millikelvin. If you look at the mass of gap generated by the magnetic exchange, it's on the scale of about 300 millivolts. So there's like a huge gap of about 3-4 orders of magnitude of where they need to cool down before they get something that looks roughly like, not roughly, it looks like a quantum Hall conductance quantization. And so I'm pointing out that this difference in the energy scales is coming exactly as a result that you need to freeze out all the states inside the gap. Okay? So then I surmise from that the search for a robust anomalous quantum Hall effect would require to overcome this headwind. Put it differently, I think we should find out what are the proper defects are and how exactly to go about it. But I think actually this element, this part of physics about induction of the resonances has been not discussed widely enough, in my opinion. Yeah.
You mentioned that you have to find out how we go about trying to raise minimize this resonance peak, right?
Yes.
So that will depend where it goes, the impurity. It can still create ferromagnetism. So in your calculation, where do you assume it's going?
Well, basically it depends on I think it's a substitutional in all of this. But we did this systematic study, so manganese, vanadium, chromium, and this was for essentially antimony telluride Ti. And I think actually the best example would be the ones where you do have a so like very little perturbation in the vicinity where the gap should open up. So the example I showed you, counterexample to what I was saying, is the one where we have a little perturbation in the density of states. This would be a good example. For instance, vanadium in antimony telluride would be a good example. And then the other one, I think it was cobalt. Yeah.
I don't know whether I can agree with the last statement. In that sense, if I just use the analogy of the quantum Hall system, where you mentioned that localization is important and mobility is important. Actually, we don't care that what is the resonance state, what really causes localization. So without that information, still we see that quantum Hall plateau is kind of well defined.
Yes.
So do I really need to know that microscopic states of this resonance impurity state to stabilize or realize quantum anomalous? If I just use quantum analogy, I don't necessarily need to know its microscopic states.
Yes, that's true. So my point is that probably what I'm saying is important to understand how we can go from 30 millikelvin to the raw energy scale, which is the 300 millivolt, okay? Because in your case, for graphene, for instance, if you do the back-of-the-envelope estimate of Landau level splitting and temperatures required to get the quantum Hall effect, you can get there if you have clean enough samples. Here we have this 3-4 orders of magnitude discrepancy. So I'm saying actually we can try to brute force it, continue actually trying to find out kind of like random samples or random platforms to realize the anomalous quantum Hall effect. But knowing what defects are doing to the gap states might be useful. So I'm not saying that there is no, certainly actually the anomalous quantum Hall effect has been observed. But I'm saying actually how do we get like increase the temperature? Engineering of the impurity response would be very useful. So maybe you agree after all, or maybe I don't know. All right, so just very quickly to tell you that Dirac materials don't have to be fermionic. Very quickly, if you have a honeycomb lattice is a non-bravais. Just like if you have a graphene, each carbon atom and vapor in the air here, if I catch a carbon atom, it's the same. All of them are identical. I put them on the non-bravais lattice, they become carbon A and carbon B. They acquire this index. They know they're sitting on red or black, okay? So if you have one electron hopping on the honeycomb lattice, the electron doesn't care about the statistics because it's only one electron. Say we have only one electron in the whole universe. There is no statistics. Now let me put one boson on the honeycomb lattice. Guess what will happen? It will develop the same Dirac cone precisely because basically tight binding Hamiltonian on the honeycomb lattice will develop this kind of crossing point, okay? So population, regardless of what the statistics is at the quadratic level, at the level of non-interacting particles, will always develop the Dirac crossing point. So hence, if I put in on this lattice bosons, I will develop the Dirac crossing point for bosons, okay? So example I will quickly show is the Josephson junction circuits and magnons. So I'll show you that actually Josephson junction sets, maybe I will show it, has the same Dirac crossing point. Let me start with the following. I never paid attention, yes?
Magnetic impurities on superconductor can also close the gap and give this kind of impurity resonance level?
Yes, absolutely. This U-Shi-Barusin of resonances, and these resonances are close relatives.
So is there any importance of where the magnetic impurity is? Like, is it like an end state or
End state?
like the one we like Majorana wire, for example? Could the magnetic impurity be? Could it be a impurity resonance state?
You're asking if Majorana resonance peaks, the peaks seen in tunneling and maybe some other spectroscopies at the superconducting wires are Majorana or not. I think actually people still debating it. I think it's consistent with Majorana interpretation. There is a lot of actually consistency arguments, but fundamentally what you measure when you tunnel into those, you do not measure the phase and you do not measure braiding properties. We all kind of know that to really establish the Majorana nature of these excitations, we need to look at the statistical properties. You just measure the peak and density of states. So I think actually depends whom you talk to. If you talk to Charlie Marcus, I'm sure he's convinced. If you talk to Coven, Leo, they convinced it's a Majorana excitation, or maybe they say it's very consistent with that. But I would say fundamentally, at the observation level, actually, we're measuring the peak and density of states. This is not even the amplitude of the wave function. You just measure the wave function squared. Okay. So I would just say this. It's a very interesting example if you look at the non-bravais lattice, which is actually, and you look at the phonon spectra, you have a Dirac crossing point. And like I said, I never paid attention to the phonon behavior. But this crossing point here is very similar to what you have actually a Dirac point in graphene, right? So for the phonons, you have two sides per unit cell. Each of the atoms has about 3 degrees of freedom, so you have to have 6 branches. So it's much busier band structure for the phonons. And here we have 1, 2, 3, 4, 5, 6 branches. And they do all sorts of crossing points and very interesting actually effects here. For instance, here they have a tilted Dirac cone. But here they have a, by and large, very similar Dirac cone to what you expect in the band structure for electrons. All right. So then another example of what we were looking at, I guess I'm not showing the Josephson junction array, but you can think about if you put the niobium grains or you put some superconducting grains into the honeycomb lattice or any non-bravais lattice, and then if you think about the tightly bound pairs, which are essentially at low temperatures, essentially Cooper pairs, like effectively bosons living on this network, one can see immediately that you will have in the honeycomb lattice the Dirac crossing point for the dispersion for the collective modes of the Josephson junction array. All right, so example I want to emphasize here is the case of the honeycomb ferromagnets. This is an example of the chromium trihalides, where it turns out that there is a Dirac crossing point. And in the low temperatures, you do have a conventional quadratic dispersion for the ferromagnetic mode, but at the high energy, you have this Dirac crossing point that couldn't be sampled. So the difference for the fermions and bosons is that actually I can live at near the chemical potential and put the chemical potential near the Dirac point for fermions by biasing it or by gating, for instance, my structure. And for the bosons, the relevant excitation part sloshes around this gamma point where the spectrum is quadratic. So technically, there is this Dirac crossing point for bosons, but to reach it, one needs to pump it or do something interesting, some other kind of drive for the system to sample it. But as a matter of fact, there's a spectrum of excitations, the Diracs, of bosons living on the honeycomb lattice will have a Dirac crossing point. So here example, this is a paper done in the 1970s where they looked at the Dirac crossing point. They knew that there is this in the chromium trihalide, which is a layered honeycomb structure where the chromium formed the honeycomb lattice. They knew that there is a crossing point. They didn't call it Dirac crossing point. This is my title. But I think they discovered in the neutron scattering there are some very interesting signatures in the vicinity of Dirac crossing point. And those are this is a particular example of the whole family of this chromium iodine, chromium bromide, and chromium chlorine with a Néel temperature ranging between 20 to 30 Kelvin, I believe, or 60 Kelvin. So when we apply the analysis to this Dirac point, we find out that the effect is when we apply the interaction of these magnons, or theory of interaction of these magnons, we find out two things happening. One, the Dirac crossing point drops down, and the other one is the dispersion curve for the interacting bosons flattens out. Now, this is something for few, if you remember, in the case of the fermions, the dispersion point, in the case of the Coulomb interaction and the fermions and the graphene, in the vicinity of Dirac point, interaction leads to the fact that velocity stiffens up. Interacting bosons, we find short-range bosons lead to the flattened dispersion. And so we were able to explain some of the signatures seen in experiment. I point out that there is interesting work coming out of MIT and others where they looked at exactly a single layer version of this honeycomb ferromagnet. And so I would say that the same Dirac magnon behavior we see in the bulk will be present in these two-dimensional honeycomb ferromagnets. Okay, this is a work done, published in fact very recently. There's a back-to-back to Nature's looking at the ferromagnets. Okay, now, so in the remaining 10 minutes, I want to switch gears and talk about the organic materials. Okay, and maybe we'll take a few minutes more on this. So, I felt like I have to give you a little bit of introduction or discussion about what I think is Dirac material is. But now the question is, so what's next? And one important direction or one important unexplored aspect of these Dirac materials is that can we, once we develop this understanding, can we look at some other classes of materials where we can have these Dirac crossing points? And then we realize that maybe organics is an interesting space. So motivation for this work is this crosstalk between the basically looking at the data, looking at the very interesting experiments, and maybe applying the computational tools. And this whole slide is taken, I guess, from Materials Genome web page, where they talk about accelerated path to discovery of new materials and new functional properties. Organics is very interesting. Why? For a number of technological, practical reasons. They provide a flexible electronic framework. They're actually very useful in technology. And what's interesting is that organics is a niche play in physics. It never was, or I would say that it probably has a smaller footprint than it deserves in the physics. My personal experience with organics was that early on I looked at the effects of the disorder in some of these Bechgard salts like TTF, TCNQ, the early on superconductors. But I think it always remains somehow like a domain where you have few enthusiasts who feel very passionate about this. But then in chemistry and technology, the organics is a very important part of the effort. So as like I said, actually, we can talk about the extension of the class of Dirac materials to organics, but broader, what we build the organics materials database, and we realize we build a very versatile tool, or I hope to convince you it's a useful tool regardless of Dirac materials. So I'm just taking off my hat as a Dirac person. Let's set it aside. I just want to tell you that we have a tool which is a computational searchable tool, which is accessible, that allows to to look at the band structures of a lot of organic materials, and maybe when we apply the large-scale calculation, we can then go and analyze this, use some data mining techniques, and find some interesting properties. The two people who are responsible for this is Stas Borisov and Matthias Gallhofer. This is the work of these two postdocs for the last 2 years, and then Stas now moved on to become a faculty. So what exactly we do about this database? We look at the crystallography open database, which allows essentially full dump of the data. And then we download we looked at about 100,000 organic compounds. And then we have some scripting where we build in, take the user input files from this database, and we do the calculations. So just to be very clear, there is a structured database, okay, where, say, chemists go out, synthesize the compound, they tell you what the crystal structure is, they publish a paper, and then actually the website has agreement with journals, and they basically have crawlers, and they take it and create the entry in the database. Okay, database itself here has about 300,000 compounds, and organics is about 100,000, I think. Then we come in and we build this electronic structure calculation on top of this, and we populate our database. The protocol, how we do it, is shown here. We do the WASP. We do very simple calculation. Sometimes we do the spin polarized. Sometimes we do the no-spin polarized calculation. And we do not take into account spin-orbit coupling. Why? For majority of these compounds is made from carbon and hydrogen, and so the spin-orbit coupling is not as crucial. All right, so then I should show you how the database works. So if you come into the web page, you will find this landing page where you find out some examples of what we can find out, or like results of what we get playing with this. So let me show you. So you go to OMDB, Organic Materials Database, diracmaterials.org. Okay? That's where you land. This is a freely available resource for anybody with academic address. You can come and register. Now we put in a little bit of a actually speed bump so that people don't come and actually download the whole database at once. Then once you register, what this tool allows you to do is to browse, for instance, for materials. So let me do the browse. So this is about, you see now it's about 25,000 compounds on the database. You come into any of those, for instance, this one. So the top part here is taken from crystallography open database. In this particular case, it's a C19H20F6 oxygen. This is how the molecule looks. This is what declare on the database is the crystal structure, alpha, beta, gamma, and the lattice parameters. And then we come in and calculate the band structure. So this happened to be wide band insulator with a band of about like 3 electron volts, 4 electron volts. Okay. Then you can download the input files for your detailed calculation or for improvements if you want to. And so the idea here is that we want to provide the resource for the quick assaying of a lot of organic data. Yeah, organic data. Then out of these 25,000 compounds, what we publish is we can look for the materials which have no gaps, and you can find out that right now we have about 100 compounds which have a very little gap or no gap at the Fermi level. So it is a true mining exercise in the sense that if you take a dart and throw it at the map, you will not be able to score it. So just to give an example of what's happening. So in this case, it's a compound that contains cobalt. Let me just click here. That's how the crystal structure looks like. So you can probably figure out that this one should be very well separated in insulating compound. And it is, except there is a very flat level at the chemical potential. And so if you want, this is a very narrow narrow band metal. And then of course, as we discussed with Philip already, it can be anywhere within a certain range. It doesn't have to be exactly at the chemical potential. So for instance, but if you, for whatever reason, you're interested in this compound, it's good to know that they have a flat band, and this flat band probably can be controlled by doping. Now, so the database allows you to do the structured search. For instance, we can look at the band gaps. So in this case, for instance, if I go in on this side for the band structure, for the gaps, for instance, if I ask for the set of materials with the gaps between 0 and 0.1, and I want to do it at what is calculated as the chemical potential, and then the energy range between, actually at the chemical potential, then we'll see how many we find. So we find about 215 compounds which have a very small gap of about 0.1 electron volt. And this is a very complicated molecule, as you can see from here. Yeah, and this one happened to be ferromagnetic. The color here means spin up and spin down, and we find out that this material is a ferromagnet. Let me see if I can zoom in. Right, so this yellow, hatched yellow or light yellow region, beige region here is exactly this 0.1 electron volt or whatever the request was. The small gap near the chemical potential, but you can see there is a lot of flat bands at this place. near 0. So now let me go back to my slides. So that's what I was telling you about the database. This is how the band structure calculation is. So this is the input we take. This is what we produce. When we produce it, actually turn by for 25,000 compounds, and it keeps going. Yes? One thing actually that the database forces you to have questions about, once you have this kind of massive amount of data, you know, like a typical organic material is an insulator, wide band insulator. The question is, what is the typical gap? What you find out, the statistics of the gaps lies out in very nice, beautiful Gaussian with a chemical potential of about 2-3 electron volts and the width of 1 electron volt. And we do have outliers which show that maybe we have a luck. There is a slightly elevated presence of the metals with small gaps. And we can have an online pattern search. So I would like to point out, so we started with organic 5 minutes. 2 minutes? 1 minute? How about -1? Yeah, exactly. Yeah, okay, fine. 1 minute. So let me just kind of quickly go through. We do find organic materials. What you find also in this, looking at this massive amount of outcomes of the band structure, for instance, the special group 14 has a lot of universally returns the Dirac points. There's plenty of non-symmetric groups like 14, 19, and others. Just like in the hard inorganic materials, returns the kind of Dirac crossing points. And those are Dirac crossing points. Those are not wild points because there is no spin-orbit coupling. Okay? And then I would just say that we also looked at the similarity search for motivated by this organic perfenyl declaration of the kind of high temperature superconductivity in organic material like a perfenyl. We looked at the similar density of states for the input for the background parameter for the background compound on which you want to do the potassium doping and presumably induce superconductivity. What we find about 15 other compounds which have very similar band structure to perfenyl. And so therefore, we hope it opens up the search space to find other compounds which would be might host superconductivity. All right. So the database has been out for about a year. We actually wrote the paper the paper came out in February, a year ago. We now have about 120 users. There's a distribution by the countries, US dominating, Sweden, China, and others. And part of the reason I'm, in spite of the consternation of Professor Westerveld, I'm just keep plowing along. I'm wearing the hat of advertiser here, right? This is a free database. What we'd like to do is actually to have a community to start using it because it provides a maybe very useful resource, we believe. We don't know how and what it would look like. So here's an example. We mined some of these materials for the very simple Dirac crossing points. For this material published first time, synthesized in 2014, for totally different purposes. This is a biomimetic copper water oxidation catalyst, but it has very interesting band structure properties, kind of Dirac crossing point with a flat band. We spoke to the organic chemists, they synthesized some vial, and then the idea would be that we're looking for somebody who can help us to characterize it, or the other way around. We can talk to experimental groups and look at the connection to what the band structure is. But we definitely would like to generate a greater usage of this database. Okay, so with that, let me finish quickly. So what I showed is that Dirac Materials provides a very simple classification, and it offers I would say, very useful guidance going forward. For instance, in terms of the transport properties, suppressed backscattering, but also impurity resonances in a lot of materials, Dirac materials viewed today. I think it's not just kind of sales tool. I think actually there is some utility in thinking about this as a Dirac or wild materials because you do find kind of as we go forward. I was surprised myself how robust the outcomes are on a lot of these Dirac materials, how they similar are. So just to show you that the universality is actually the Dirac point you sample in graphene is about below 1 electron volt, and closer, maybe a fraction of electron volt Dirac point in the D-wave superconductor is in the scale of about 50 millivolts. So energy scales are very different, but the statement is there is energy scale below which you're beginning to see universal features of the Dirac node. And then for the organic materials database, we have about 25,000 compounds, an open source tool. and research for the materials community. So with that, thank you for your patience. So,
Okay, just few questions if you have any. So just about the impurities. So in the couplets, there are usually to get superconductivity, you add oxygens, which are basically impurities. So what is the difference between the what is the difference between those impurities that are good impurities
and bad impurities, yeah.
Bad impurities?
Exactly. Dopants are also impurities, absolutely, yeah. So this is a very complicated story. I'm not sure I know exactly what the status is, but maybe somebody in the room. So my take is that it really depends on the actually scattering strength in a way. So oxygen, we believe, oxygen you need to put in the carriers in the cuprates. Oxygen can come in to be actually off the site where the superconductivity itself develops. So it just basically predominantly the role is to donate the carriers and not to perturb the motion of electrons. So remember this Klein paradox. If you have a smooth enough profile of potential, if you take impurity offside, which provides kind of smooth variation, it probably will be less of a pair breaker. So the point actually, this resonance is a function of the strength of the scattering. It doesn't have to be exactly the nodal point. It's a very simple function. It's never, very rarely exactly mid-gap state. People talk about mid-gap state. I find it is intra-gap state. It doesn't have to be exactly the middle.
Yes, you probably excited these resonances with electromagnetic radiation, like terahertz radiation.
Yes, so that would be one. For instance, another kind of, you're talking about observables. First of all, you can see them in STM, but another place where it might be very useful is electromagnetic radiation. And the third one I find, they come in inherently at the particle Hall asymmetric actually excitation near chemical potential if you have a fully compensated state. And so they will probably provide very large contribution to thermal transport because the holes and the carriers will carry different, you have a very different conductance for electrons in holes.
Any last question? I have a question. What's your take on topological superconductors?
It's a very good take. So, by the way, I forgot to say to the people who are here, maybe I can ask you to pass around like in the last minute. I have few leftover slides, not slides, but the posters for the, just pass it in the audience. Yeah, this is actually the advertisement for the database. So for superconductivity, I think actually, yeah, it would be very interesting. I mean, this is clearly a very interesting effect, and actually all these topological properties of the superconductors marry essentially the best of the worlds. You have a topology and you have superconductivity. So it should be very exciting.
Thank you. So I think with this, we'll thank the speaker for coming down here.
So there is a class next.
I have a quick question.
Yeah?
So for your organic materials database, for a lot of those organic species, like
Yeah.
crystal structures have never really been done. So
Well,
do you guess, or how do you do it?
no, the papers